This week we're going to be discussing the Poincare Lemma, which concerns the relationship between closed and exact differential forms. So before we state it, we need to define what closed and exact mean. So we say that a K-form on a manifold M is closed if its exterior derivative is 0. And we say that alpha is exact, again, alpha is a K-form on a manifold M, if alpha is equal to d of beta for beta some K minus 1 form on the same manifold M. So notice that if alpha is equal to d beta, so say alpha is exact, then this implies that d alpha is equal to d beta, which is equal to 0 because when you apply d twice, you get 0. So that means that alpha is closed. So exact always implies closed. But does closed always imply exact? So in general, no. In class and on your worksheets, we'll discuss some examples. The simplest examples are just forms on the circle. There are differential forms on the circle or equivalently on R2 minus a point, which are closed but not exact. And the theory, or so the difference between closed and exact forms is behind a lot of higher level topology. But we're going to be studying first differential forms on Rn. And the Poincare lemma is going to tell us that on Rn, closed does imply exact. So for k greater than 0, so this doesn't work for 0 forms, if alpha is a k form on Rn, and if it is closed, then it's exact. One major use that we're going to make of this is we're going to learn a theorem called Stokes' theorem, which is a generalization of the multivariable calculus Stokes' theorem. And in that theorem, integrals of exact differential forms can be simplified tremendously. So because it's easier to check whether something is closed than to check whether it's exact, the Poincare lemma will be very helpful in that situation when we're trying to apply Stokes' theorem. Okay, so let's outline the proof. All right, I'll leave the lemma there. So we're going to be proving the method that we're going to be using is induction. And the base case is going to be basically all differential k forms where k is greater than 0, but when n is equal to 0. So notice that R0 is just a single point. So it's all sort of, it's all 0 tuples of numbers. So there's just sort of the empty 0 tuple. And in this case, when k is equal to 1, so we're going to show the base case for k equal 1 separately for k greater than 1. So the only one form is the 0 form because 1 is greater than 0, right? If you're looking at k forms where k is greater than n, then you have none. And they're all closed because the only 2 form on R0 is also the 0 form. So it remains to show that they're all exact. So what are the 0 forms? So the 0 forms on R0 consist of functions just from a point R0 to R. So i.e. just numbers. Basically every function is just a number. All of these functions don't vary because they're just constant because R0 consists only of a point. So d of such a function is always 0. So alpha is equal to 0 and it's equal to d of any function from R0 to R. So alpha is exact. When k is greater than 1, basically it's the exact same argument, except the only function, or the only sort of k minus 1 form I'm allowed to consider is the 0 form. But still, I don't have to worry, because in this case, I can just basically just do the exact same thing I did for k equals 1. If alpha is a k form on R0, it's the 0 form. It's closed by the same reasoning as for 1 forms. And again, the k minus 1 forms on R0 consist only of the 0 form. Because the 0 form doesn't vary, d of the 0 form is equal to the 0 form, but that's all I have to worry about, right? Alpha is the 0 form. Okay, so that's great. So that's our base case for our induction. So the way that we are going to explain how the inductive step works is going to, it helps to draw a diagram. So basically, we're going to use that the Poincare lemma is true. So this is our inductive step. We're going to use that the Poincare lemma is true for all k and up to Rn. So for n, just for all k forms on Rn, and then prove Poincare lemma for k forms on Rn plus 1. So it's helpful to kind of visualize this as a diagram. So if I have all my forms on R0 on this side, etc., so I can continue this. D goes this way, and then I'm going to draw all of my all of my 0 forms, 1 forms, and 2 forms on R1, so etc. And I can include columns for R2, R3, etc., but I'll just draw the column for R2 and then let you imagine the rest. So there's going to be even more, right? And the point is the proof, the inductive step is going to use the proof from, so I'm going to denote it with a red arrow. It's going to use the proof for the same k, but 1 less n. So the inductive step is going to sort of prove in this direction. And then we'll prove the Poincare lemma for all k and all n. So we already know it's true for all of these. And so we just sort of go right in the diagram. Okay, so the proof is going to use 3 maps that we'll explain in this video, and then I'll explain the proof in the next video. So the first map is called the stretch map. So this map goes from S, it's called S, and it goes from Rn to Rn plus 1. And what it does is it takes a point x1 through xn to just x1 through xn 0. So basically includes Rn into Rn plus 1. And it induces, of course, its pullback. And we're going to give its pullback a name, curly L. So that's going to go from k forms on Rn plus 1 to k forms on Rn. There's also going to be a projection map. So this is going to be called P from Rn plus 1 to Rn. And it's going to take y1 through yn plus 1 down to y1 through yn. So basically you just forget the last coordinate. And this is going to induce curly C. I'll make that look more like a C, which is P pullback, which takes k forms on Rn and turns them into k forms on Rn plus 1. So how are we going to use these two? So the plan, I said there were going to be 3 maps, but we'll talk about the third one in a moment. So if alpha is closed, then let's consider what d of L alpha is. So alpha is a k form on Rn plus 1, and I'm going to consider what d of L alpha is. So this is going to be a k plus 1 form on Rn. So d of L alpha is d of s pullback alpha. Because pullback and exterior differentiation commute, this is s pullback d alpha. But because alpha is closed, this is just 0. So, I mean, I can spell it out. It's s pullback of 0, which is 0. So this means that L alpha is closed. But L alpha is a k-form on Rn, right? So alpha is a k, let's assume, I should have said this from the top, alpha is a k-form on Rn plus 1. So we're going to be proving alpha is a k, the Poincare lemma for k-forms on Rn plus 1, assuming it for k-forms on Rn. Alpha is a k-form on Rn, so by the inductive hypothesis, L alpha is exact, right? Because if L alpha is a k-form on Rn and it's closed, then it's exact by the Poincare lemma. So I'm going to write L alpha as d of beta for some beta, which is a k-1 form on Rn. Now let's consider CL alpha. CL alpha is C, that's an L, not a C, C d beta. And this is P pullback of d beta. And P pullback of d beta is d P pullback of beta, which is exact. So our goal for our proof is to relate, oh, and I guess sort of the, L alpha is also exact, but the nice thing about CL alpha is that CL alpha, right, so L alpha was a k-form on Rn, but CL alpha is now again a k-form on Rn plus 1. So we can relate CL alpha to alpha. And this is exact, and we want to show that the difference between these two, CL alpha and alpha, is also exact. So to do this, we're going to define one final map. We're going to call it K. So K is going to take k-forms on Rn plus 1 and turn them into k-1 forms on Rn plus 1. And it's going to be given term-wise. So a sub j, y1 through yn plus 1, dyj. So j is some k-tuple from, ascending k-tuple from 1 through n plus 1, is going to go to 0 if jk is not equal to n plus 1. So if there are no y sub n plus 1s, dy sub n plus 1s in this term, I just get 0. And if there are, then k sends this term, aj dyj, to the integral from 0 to yn plus 1, a sub j, applied to y1 through yn, t, dt. And then that is going to be the coefficient of dyj1 wedge all the way out to dyj k-1. So I basically just remove the last y sub j, which will only happen, remember, if y sub j sub k is equal to n plus 1. And then we extend it linearly to alpha, which is equal to the sum over j in I k n plus 1 aj dyj. So the strategy of our proof is going to be to show that alpha is actually equal to CL alpha plus -1 to the k-1 times dk alpha plus kd alpha. And this actually is going to be true for all k-forms on Rn. We've shown that this first term is exact. The second term is exact because it's d of k alpha. And this term is just 0 because alpha is closed. So that's going to be our strategy, and we'll explain how to complete the proof in the next video.